40. So just a couple of administrative things before we dive back in. Midterm is obviously this Thursday. I believe it's 277 Corey, but I posted it up on Piazza, so double check there for the exact location. Again, it's 6:30 to 8 p.m. Sharp, so make sure you come there and we'll start on time. It's open book, open notes. They may or may not help you all that much, but you're free to bring anything you want there. Just know, obviously, typing on the internet, talking to your friends or anything like that. Other than that, I will also be doing the review session tonight. That's 6 p.m. Just over in 550 Corey. And again, just come with your questions and I'll answer them. So other than that, any questions either on midterm, homework, lecture material, anything like that? All right. If not, then let's go ahead and sort of dive back into our material. So last time we were talking about sort of the folded Cascode OTA. And we sort of started down the path of kind of doing some characterization of the OTA. And I think where we basically ended up was looking at the low frequency gain of the particular structure. So we spent some time talking about how if you actually looked at the curve that I've plotted here, which is just the sort of both small signal and large signal gain versus the output differential voltage, we said that actually the swing was larger than the power supply. And we said that actually no physics was being broken there because it's a differential circuit. So of course, if one side can swing, from V to D to ground, and the other side can also swing from V to D to ground, at the end of the day, you can indeed, at least theoretically, get double the supply voltage in terms of swing. So that's, very commonly one of the sort of advantages people quote for differential circuits. Now, having said that, if we kind of take a step back, if you remember, we had said that typically the way we're going to sort of spec things, or sort of one of the specs that we're really going to care about was basically how large of a voltage swing you really could get as a function of kind of the gain we wanted to make sure that we maintained, right? So as an example, in this particular case, if I wanted a small signal gain of greater than 100, we said that gave us something like, I don't know, whatever it was, 3.8 volts of swing or something like that. So if you sort of look carefully at these curves, you'll see that everything is kind of totally symmetric, right? If I go on the, let's say, negative output voltage versus the positive output voltage, everything kind of looks the same. Now, that's very sort of, let's say, to be expected, or really that should be the way that things are, because we are talking about a differential circuit here, right? So anything that I sort of, if I have a negative output voltage, then on the other side of the circuit it's positive, right? And if I flip it, the exact opposite thing happens, right? So there really should be no sort of asymmetry in this curve. Now, the problem with that is that, let's say that this swing is not large enough. You actually want to go ahead and improve it. If you really just look at this plot, you may not actually be able to tell which transistor or set of transistors is it that's really dominating your overall swing characteristics. So because of that, what you'll typically actually want to do is plot not just that net sort of gain curve, but you actually may want to split things out to look at, for example, the NMOS and the PMOS devices independently. So for example, this blue curve here might be the RO of the NMOS devices as a function of the output swing, and this pink curve here might be the PMOS output resistance. Okay? So again, the real key point here is that only if you plot those two independently will you actually be able to tell which one of them is really dominating the overall swing range, if either one of them actually is. Because again, if I look at sort of the parallel combination here, and I do that, especially in the sort of the differential context, it'll really be totally symmetric, right? And you wouldn't be able to tell if, for example, as the swing is coming down here, is it that the NMOS is crapping out too early, or as the swing is coming up, that the PMOS is crapping out too early relative to what you would want it to maintain. Okay? So again, the sort of take-home message here is just make sure that you indeed, when you are characterizing these amplifiers, when you're trying to design for a certain spec, actually pick off independently the NMOS versus the PMOS section so that you can indeed have an idea of which one really is dominating you more heavily in terms of the actual swing range you're able to achieve. Make sense to everybody? Or? Okay, so just a couple of sort of short things that I want to mention before we wrap up really talking about this folded Cascode OTA. The first one is that oftentimes it turns out you're actually going to want to add an additional Cascode into the input stage. Okay? Now, oftentimes when I first show this, people kind of look at me funny like, what the heck? Why in the world would you want to do something like this? Okay? Well, in order to kind of motivate that, let's sort of think a little bit more carefully about what cascodes sometimes actually bias. Okay? So I'm going to actually argue that oftentimes, even if I ignore sort of the folded structure, even if I do a very simple resistively loaded amplifier, something like this, oftentimes I'm actually going to want to add a cascode even to that resistively loaded amplifier. Okay, so as an example, this is my Vout, this is, let's say, some bias, and this is some input. So let me ask you guys, if I really have a resistively loaded amplifier, and by the way, when I say resistively loaded, that's kind of implying the gain is not going to be super high, right? In other words, the output impedance is going to be fairly low. But nonetheless, there is going to be some gain in that structure. So why might I want to add a cascode to this, very, very simple kind of amplifier here? What's one of the reasons that that cascode is actually helpful? Yeah? The input cap isn't what? There we go. That's exactly the trick. Okay, so remember, if I just had a very simple common source amplifier like this, right, then that CGD is going to end up being effectively multiplied by the Miller effect, right? Because whatever gain I have across that structure will effectively increase that input capacitance. Okay? Well, indeed, one of the main, or maybe one of the nice benefits of a cascode is that to the extent that that source node there is indeed a low impedance node, the gain across there should be low, and therefore you really shouldn't be paying much of a penalty on that CGD. Okay? So that even in something like this common source resistively loaded amplifier, or maybe you didn't want a ton of gain, you wanted to add the cascode in simply to reduce the basically multiplication of that CGD. Okay? So it's going to turn out that actually this is going to be exactly the reason we're going to want to do this here. But again, in order to make sure we understand why that is, we have to maybe do a little bit of a reminder. Because let me maybe ask you guys a question to see if we can pick off why that at first maybe seems a little bit funny. Okay, so let's say we go back to this original folded cascode OTA, where here I do not have that input cascode. Okay? So oftentimes, people look at this and say, well, I don't get it. Why would you add a cascode into the input device? Because, hey, we already have a cascode over there on the output, right? So the input device is already going into a cascode. So the question that often comes up is, well, so if I already have a cascode, don't I already have a low impedance at the source of that cascode node, right? And if I have a low impedance, then why would I need yet another cascode? So now let me ask you guys, what's the flaw in that argument in this particular structure? Why is it that indeed you might actually really need another cascode if you really want to get rid of that CGD? Or at least get rid of the Miller multiplication of that CGD? Give you guys a little bit of a hint. What did we say was always the relationship between the swing at the output of a transistor, or rather I should say at the drain of a transistor, and at the source of a transistor? What was that relationship? Or rather, how much bigger was the swing on one side versus the other? This is something I told you guys to remember back, 3-4 weeks ago or something like that. How much isolation does a cascode really add? I heard somebody whisper something. There we go, GMRO, right? Okay, so now let's go back. Well, actually, let's even look at this picture. So if I look up into that stack of PMOS transistors there, right? How high is the output impedance? Roughly speaking. Well, okay, vary, but in terms of GMROs, let's say. Okay, right. So let's not ignore the 1 plus just because I'm lazy. It's basically GMRO squared, right? Okay. Well, if that is GMRO squared, that's implying the swing up there is like GMRO squared times the input GM, right? Well, okay. So if I now look at the source node, one cascode below it, how big is that swing? What's it proportional to? Yeah, it's proportional to just RO, right? That's still pretty high, right? Maybe it's not super high, but that could easily be a factor of 4, 5, 10, right? So in other words, if I really wanted to make sure that that CGD, which of course would be sitting right here, does not experience a gain from this point to this point, I need to add yet another cascode, right? Which is exactly what I've done in this picture right here. Okay? So again, the really critical thing to remember is that just because you have a cascode does not mean that at the end of the day you have a low impedance at that node. Okay? Because again, you always only get a GMRO of isolation there. Okay? So in this particular example, because the load itself is very high impedance, that therefore means that I still actually have a high impedance here. Okay? And by the way, this is maybe something that you guys should do for your homework because it's actually a quite useful thing. But I think I may have even mentioned this once. If you look into the source of a cascode, and let's say there's some generic RL on top of it, what you'll typically get in terms of the impedance is 1 over GM plus RL divided by GMRO. Okay? So that means that even if the GM is really, really big, you're at most going to get a GMRO of reduction versus the output impedance. Okay? So again, keep that in mind because that can indeed actually cause problems, especially in these kinds of structures. Is this clear to everybody? Or? Okay, great. So one other thing that I want to just spend a little bit of time on, especially because it's going to lead nicely into our next topic, which is going to be talking about feedback, is that you have to be pretty careful when you put these structures together because there's some fairly innocuous things that you can do that turn out to actually potentially cause some fairly major problems. Okay? So just as an example, let's say indeed I took this folded cascode OTA, and let's say that, okay, well, I didn't follow my own advice. I didn't put a cascode on the input this time, but, don't worry about that. We can always add that in later. Let's say that I really wanted a good current source in my input stage. So I said, okay, fine, I'm going to use a cascoded current source for that tail right there. And hey, I needed a cascoded PMOS current source over here, so why don't I just tie these bias voltages together? Okay? Well, turns out that by doing that, we can actually introduce a very interesting feedback loop. Okay? So before I go too much farther, let me ask you guys, what kind of feedback loop might have I been introducing by simply doing this very, this very innocent thing of saying, well, hey, I needed a cascoded source here, cascoded source there. I'm just going to tie the biases together. How can that potentially cause a feedback loop? And in which kind of signal would the feedback loop exist? There we go. There's a common mode feedback loop. Okay? Because differentially speaking, everything is symmetric, right? So you can't really be doing anything on the differential loop. But common mode, there's absolutely a feedback loop. Okay? So just to be clear, where would that feedback, what elements need to exist or what parasitics have to exist in the transistor for you to get a common mode feedback loop out of this structure? What do you guys think? By the way, this whole loop exists because I tied the biases together. So there's going to have to be something that's connected to the bias lines. Yeah, there we go, CGD. Okay? So if you think about it, all of those transistors are always going to have a CGD. Right? And even though I said this is some bias voltage, in reality, it's always got some finite output impedance. Right? Okay, so I've got a CGD in this transistor here. Of course, I'm also going to have a CGD in that transistor there. And of course, I'm going to have CGD in this device, that device, this device, this device, and so on and so forth. Okay? So now let's just do a simple thought experiment. Let's say some, cosmic particle comes in and basically hits your circuit, and just so happens to make this bias voltage go higher than it used to be. Okay? So what I want to go through is just walk through, which direction every single node in the circuit gets moved due to that, to see what kind of feedback we're going to end up with. Okay? So again, let's say that gate goes high. What's that going to do to the tail node of the input pair? which direction is that going to move? Is it going to move up or move down? Okay, I saw a couple people pointing in the right direction, but maybe just speak up. Is it going to move up or move down? Again, the gate of a PMOS transistor, which is the current source, went up. Yeah, so it's going to go down, right? It's a common source amplifier. This tail node here is going to go down, right? Okay, well, so if that goes down, what's going to happen on the sources of those two NMOS transistors there? In other words, what's going to happen to the common mode? Yeah, they're also going to go down, right? Okay, well, if those go down, what happens right here at the output, common mode-wise? Yeah, it also goes down, right? You're just going through a cascade, so no sign inversion. Okay, well, then, of course, finally, if that happens over there, that's also going to happen on the drains of those two transistors, right? Which finally means that when we finally close the loop, that one is going to go down. Okay? So I would sort of argue this is somewhat of a good news, because it says that at the least we have negative feedback, right? In other words, if due to some external reason this node went up, because of the connections we introduced here, the sort of feedback is going to come back and be of the opposite sign, right? So I claim at least initially that's good news, because we could have actually had positive feedback and then we'd be like really scared, right? But even with this, I say, my argument is that we still have to be very careful. So what's like the number one thing, again, you always have to check with a feedback loop? Yeah, stability, right? So even though this is negative feedback, if I have enough poles or sort of closely spaced enough poles in that feedback loop, it may not actually be that stable, or maybe marginally stable, right? So by the way, what would be really bad if, let's say indeed that actually that feedback loop was unstable? What would happen to the circuit? How would it behave? Say that again? That's right. You wouldn't have the correct current bias. It's kind of actually, in some sense, even worse than that. So again, if I take in any sort of system and I make it unstable enough, what does it tend to do? Yeah, it oscillates. So in this particular context, it would mean that the common mode would oscillate, right? So the common mode would basically oscillate, for example, between 0 and VDD, right? Maybe not exactly that, but close, okay? And as should hopefully be clear, if your common mode was oscillating between 0 and VDD, differential mode unlikely to actually do anything particularly useful, right? Because the whole thing is just not biased properly. Okay, so again, key point here being that you have to be really, really careful, because particularly on the common mode, you can get some very, let's say, innocent-looking connections could actually cause all kinds of new feedback loops you haven't even thought of. Okay? So there's really sort of two take-home messages there. One is, make sure you actually think very carefully about what feedback you could be creating, A. And B, make sure you absolutely check the common mode, right? Because if you don't check the common mode, you could very easily have this sort of badly stabilized feedback loop and not even know about it until, of course, you built the chip and it came back and didn't work and you get fired and et cetera. Okay? So one other thing that I did want to mention here is, in this particular case, we kind of got quote-unquote lucky in that it turned out to be a negative feedback loop. But it turns out there's actually a very simple way to make this become a positive feedback loop as well. And again, it's sort of very innocuous. Okay? So let's just say that I actually needed more gain than I got from this one structure here. Okay, let's say I actually needed another gain stage. All right, and let me maybe draw this in a different color here. Okay, so let me do it like this. So I'm going to build that extra gain stage. Just as an example, I'll build another, let's say, common source amplifier. Okay? And just again, because, hey, why not? I'll bias that current source for the common source amplifier using the same bias once again. Okay? So now notice, if I track through the same feedback loop, then, of course, when this input goes low, the output there is going to go high. And guess what? Because of the CGD, now the bias node is actually going to go high, right? So now notice we have something that's even more fun, which is we've got both a negative feedback loop through here, right? And we now actually have a positive feedback loop through here, okay? So just because this is something that, people like to ask on interview questions or prelims or other things that, some of you guys here may actually care about, let's think a little bit more carefully about this particular configuration or this particular situation where we actually have both positive feedback and negative feedback. Okay, so to think about that, let's say more generically, let me just draw, let's say, the kind of control theory kind of picture, and let's see if you guys can pick off what needs to happen in order to make sure that you at least don't have positive feedback. Okay? So let's draw sort of, again, our generic structure. Okay? So as an example, I have one loop or one feedback connection, which is a negative feedback connection through that F1. But notice that I put the negative sign there. But now what I'm going to do is I'm going to add to it a positive feedback F2. Okay? Which, by the way, is a really good model for the situation we have here, right? Because we have two paths, one with negative feedback and one with positive feedback. Okay? So if I want to make sure that I actually have net negative feedback, what do I have to make sure is true? What condition do I need to have with these loop gains here? Yeah, exactly. I better make sure that F1 is greater than F2. Right? Because at the end of the day, the net gain I have is, of course, just minus F1 plus F2. And if I want that whole quantity to be negative, I better make sure the negative feedback gain wins. Right? All right, now let me ask you guys. In the particular configuration I drew here, what's more likely? Am I more likely to have net negative feedback or net positive feedback? Let's maybe take a vote to make sure everyone's paying attention. So who thinks you're more likely to have net negative feedback in this particular multi-stage, with shared biasing thing? No votes for negative feedback. Okay, one vote for negative feedback. All right, good. Who votes for positive feedback? Okay, so sorry, Philip. The positive feedback guys were actually correct, but it's good that you actually voted. So, why is it probably positive feedback?
Swing on the cascode PMOS.
Uh-huh. Yeah, exactly. So notice the whole trick here is that I had a certain gain to get to this point, right? I then go through yet another gain stage to get to this point, right? And so even if I didn't have isolation from the cascode, I would most likely have more gain to this final output than I did to this point. And so because of that, the gain that would be causing the positive feedback would probably be larger than the gain that would be causing the negative feedback through that path. Okay? Now, by the way, of course, I could keep on adding more and more stages and flip which one was positive and which one was negative. But as you can imagine, if I do this too much, then I can pretty easily end up with situations where on the net, I have multiple of these feedback loops, and in the end, one of them may indeed be very unstable. Okay? So again, you just, take home messages, user beware, because you can do some very sort of simple, innocuous things that at the end of the day could actually cause a very big problem. Okay? Yes?
So in this case, the swing is sort of, I guess, not necessarily what the gain is going to be, because I guess if I'm just thinking about like the single device versus cascode, cascode time and more gain.
Oh, well, so we have to be a little bit careful here, because notice that whatever gain I got from basically this point to here, right, I'm just going to take that gain and multiply it by the gain of this next stage to get to this point.
Oh, okay.
Right? So, in fact, to make life even worse, in this particular case, if I really had a cascode here and not there, there'd be some isolation between this node and that node, which would make the negative feedback even smaller. Whereas, in this case, I don't have any isolation between the output and sort of the drain of that PMOS device. Right? The output is the drain of that PMOS. So that would directly couple through CGD, and again, make it much more likely for the positive feedback to actually win. Okay? Even if I added a Cascode back in here, still positive feedback is likely to win just because you have the extra gain stage. Okay? Now again, let me maybe ask you guys, so what would be like a simple way to fix this problem? Let's say indeed you ended up with positive feedback with that particular connection. How do you fix it? Let's see if somebody other than Paul. Yeah.
You could just put like a filter on the bias line to reject any
Okay, so you said put a filter on the bias line. What kind of filter do you want to put?
Low pass.
Low pass. Okay, so just tell me exactly how you want to do it. What you're saying is actually not is a pretty good idea, but I just want to make sure we draw it the right way.
Well, my first thought was if you just put a big capacitor.
Oh, okay. So you wanted to put a big capacitor here. Okay, actually that's not a bad idea. That's in fact actually a pretty good idea. Because notice what you're really doing by putting a big capacitor there is you're trying to say, well, look, screw it. Even if it's positive feedback, as long as the gain was less than 1, maybe I don't actually care that much, right? So I'm just going to try and put a big, huge cap here to suppress any of those coupling effects, right? That's indeed actually a very good idea. Okay. Other sort of tricks that people like to play let's say in the context of putting filter in is to, for example, put a resistor there, right? Just to low pass whatever the positive feedback coming back is. But again, user beware because you have to really carefully place that, A. And B, you also have to make sure that sort of this local node here on that PMOS device doesn't get messed up from an impedance standpoint. Because as we'll actually talk about a little bit later on, adding a resistor into the bias like this of a PMOS transistor is a great way to create pole zero doublets. Okay, and actually we'll intentionally do that later on down the road, but in other cases you may not actually, you may not want to do that. Okay? But so your first solution of indeed just putting a big cap on that bias node there, that's generally a good thing to do. Although we may have to be a little bit careful. You may have to put so big of a cap there that, that maybe is not always the ideal thing to do. So any other ideas? What else could you potentially do? And let me just redraw the line I got rid of a second ago. Any other ideas? Yeah.
It'd probably screw up your swing, but you could put like 2 more PMOS cascodes on the top, so that like.
Oh, so you want to put like extra cascodes here?
Yeah.
Oh, okay, yeah, that's true. You could do that. As you said, the swing maybe would be sacrificed by doing that, but that's not necessarily a bad idea. Anything else you could do? By the way, there's a really, really simple solution. Yeah.
Just make that last CS stage driven by a PMOS.
Oh, I see. So you wanted to flip over which one was which. Oh, okay, I see. So you want to make it so that the gain is actually coming from a PMOS rather than coming from an NMOS. Is that what you're saying? Okay, that is true. You could potentially do that. That works. You have to be careful, of course, with how we bias the NMOS now, because I said nothing about where that came from. But indeed, that's a reasonable thing to do. Any other thoughts?
Can you couple that and bias it to something else?
Yeah, there we go. That's probably the easiest one, right? If we just break that darn wire there, we have, for example, one current mirror that would generate this, and then just use a separate current mirror to generate that, right? And then as long as those current mirrors are reasonably isolated from each other, again, that would largely get rid of this problem, okay? So by the way, almost everything, or pretty much everything you guys mentioned are all valid potential solutions. I just wanted to get to this particular one because, as you can imagine, separating the current mirrors is usually a pretty easy thing to do, okay? So that's usually sort of the default way you would do it. Okay, great. Any other questions on this? Okay, so now that we actually had that sort of introduction into feedback, let's go ahead and actually move on to the next set of lecture notes, which is where we'll really more explicitly talk about feedback. Okay? Now, I should mention a couple things before we really dive in here. So, I'm going to assume that you're actually reasonably familiar with feedback, kind of at the level of, let's say, 140, or 105 and 140. And so I'm not going to spend a lot of time sort of hammering on, all of the different, Bode plots and phase margins and gauge margins and things like that. And by the way, if you need a little bit of review of that, Gray and Meyer is a great place to go look. Razavi has some nice discussion about feedback. The Tom Lee book also has some very nice discussion of feedback. So again, if you need kind of a brush up on that, those are good places to go and look. So what I really want to focus on here is basically 2 things. The first is stability, and not so much, again, to really review things you've seen before, but rather maybe to emphasize some things that you may not have thought about in the past. Okay? And the second, which we'll probably, or we'll hopefully get to by the end of the lecture today, or at least start on, is actually settling. Okay? So what I mean by settling here is that oftentimes we're going to be using these feedback amplifiers in the context that we actually want to look in the time domain and make sure that our output voltage settles to a particular value very, very precisely. Okay? So in order to do that, we're going to have to think really carefully about how closely, what the real time domain evolution of the signal will be, and basically how long you would wait, or equivalently, how much gain bandwidth you need to ensure you will settle to a certain voltage. Yes?
Is there any particular method you would suggest for analyzing feedback when there's like drawing transfer diagrams and like double projection to do analysis? Is there a particular method that you think works?
Okay. So the question was, is there a particular method that I would recommend for doing feedback analysis? I'll say some more about that in 1 second. But the short answer is not exactly, or not really. And I say that only for the following reason. It turns out that different methods get you to the answer most quickly in different situations. Right? In some situations, it's really easy to just look at a circuit, say, look, this is the equivalent block diagram. I immediately know what the answer is. Right? In other situations, it's easier to just sort of inject a voltage source or current source somewhere, track it through the loop, and measure what the response is. As you may have been hinting at, there's certain situations, particularly in simulation, where it's actually pretty hard to break the feedback loop correctly. And there's actually some other tricks that you have to play. And again, I'll talk some more about that as we go through the lecture here. Okay, so before we sort of really dive in too much into that, there's one sort of, or really just a couple of reminders that I want to give you here. So in order to give you those reminders, I'm just sort of showing here the generic feedback circuit. Again, this is almost from, let's say, the control theory standpoint, right? So I have some forward open loop gain, AV. I have some feedback gain, F, right? Or oftentimes I'll refer to that as a feedback factor. And I have some loop gain, T, which is just AV times F, okay? So if I really looked at the closed loop gain of this structure, as I'm sure you guys have all seen, many, many times before, that closed loop gain is just AV over 1 plus T, right? Or really, to say it in another way, which is often people are more familiar with, that's just AV over 1 plus AV times F, okay? Now again, just as a real reminder, if you really think about what feedback buys you, there's lots and lots of benefits that people sort of quote, but at the end of the day, the only thing that really is a sort of fundamental benefit of feedback is that it basically allows you to set the closed loop gain very precisely. Okay? Everything else, it turns out you can actually get just as well from an open loop amplifier. All right? So the real only benefit is it allows you to set the closed loop gain. And as you've hopefully seen before, the way you could sort of see that is I can, let's say, factor this equation out to put the 1 over f in the front. And then what you'd see is that you'd get 1 over f times 1 over 1 plus 1 over t. So that, of course, if t is very large, that whole thing basically just becomes roughly 1 over f. Okay? So again, the only really fundamental benefit of the feedback here is really that we're setting the closed loop gain based upon this f, and not based upon the actual voltage gain or open loop voltage gain of the amplifier itself. Now, by the way, why is it that it's typically easier to control the gain through this F factor than it is through the forward open loop gain of the amplifier? What's the sort of physical difference there in how you implement things, or what sets those quantities? Yeah, exactly. So the whole trick here, the whole reason why this buys you something, is that this feedback factor here, if you want a gain of greater than 1, that feedback factor is less than 1, right? And it's pretty easy for me to get feedback factors, or let's say gains less than 1, by just doing divisions between otherwise identical components, right? So in other words, if I build this feedback factor, for example, out of a resistive divider, capacitive divider, or any other really type of divider you can think of, what that basically means is that as long as my components match, I indeed can build a very precise division, right? Whereas to get gain, well, typically that means I need an active circuit. That then depends upon some GMs and Rs, or GMs matching some other load resistors, and so on and so forth. Okay? So this is really indeed the reason that, if you want to set a gain precisely, doing it through a feedback like this is usually the best way to do it. Okay? Does this make sense to everybody? Or? Okay, so another just sort of warning that we've talked a little bit about, but again, just I want to make sure I remind you guys, is indeed it's oftentimes attractive to kind of think of feedback circuits in this context of sort of the AV forward gain and the F in the feedback. But you have to be really careful when you map this to an electronic circuit. Okay, because oftentimes the sort of circuit and what you'd immediately sort of try and derive from the circuit in terms of the gain and the feedback factor is not really what's actually happening in the circuit itself in terms of matching to that block diagram. Okay? So in order to sort of make sure that's clear, again, let's look at this simple example which we talked a little bit about before, but just to make sure that everyone remembers what we're saying here. Okay? So let's say I took this sort of inverting op-amp configuration, and I tried to map it to that block diagram we had drawn before. Okay? So let's say I have some amplifier, of course, with a gain of AV. So okay, I'm going to put that in my forward path, again with a gain of AV, in this case, negative AV. Okay? And then I'm going to ask the question, well, if I looked from V out back to the input of the amplifier, what is that feedback factor? Well, as you guys should hopefully be very clear, right? If I look from V out back to the input of the amplifier, I just have a resistive divider, right? So that feedback factor is just R1 over R1 plus R2, right? Well, so now is where we sort of run into this problem of mapping from block diagrams to circuits. Because if I took then the closed loop gain of this block diagram, it should be minus R1 plus R2 over R2, right? Which is not the closed loop gain of this structure, right? The closed loop gain of that structure is, of course, well, why is it not giving me a color? There we go. Is, of course, minus R2 over R1. So you guys tell me, what's the problem? What's wrong with, the picture that I drew on the right? And let's see if somebody else can get it. If not, I'll bug you. Yes?
There's extra attenuation from VI to a plus net.
Yeah, exactly. You don't go directly from VI to the input of the op-amp. What you actually did, you go through an attenuation block first, right? So in particular, by the way, and let's redraw the block diagram now, what is that attenuation factor you go through? What's the value of that attenuation? Yeah, exactly. It's just R2 over R1 plus R2, which, by the way, is, of course, just the resistive divider in the other direction, right? So indeed, now if you do that, and then you apply the same block diagram that's shown on the right over there, which I'll just redraw here for the sake of clarity. All right, so you have this system now. Then everything works out. Okay? And the reason that happens, by the way, is that this attenuation just so happens to be R2 over R1 times F. Okay? And so because of that, when then it goes through the feedback structure, indeed you end up with the right overall closed loop gain. Okay? So again, the take-home message here is just be very, very careful when you map from a circuit to a block diagram. Because again, there can very easily be these additional, for example, attenuation factors in the front. There can be additional feed-forward gain terms. There can, in fact, even be multiple nested feedback loops. So just again, user beware. The mapping may not always be quite as straightforward as you may first think that it is. Okay? Okay. So with that in mind, now let's really sort of dive into the sort of heart of feedback, particularly for the discussion today, which is, again, really all about stability. Okay? So let's say I go and I give you this circuit right here, or actually more generally pretty much any circuit, but let's just start with this particular circuit that I've drawn. Okay? And so now I want to ask you guys, how are you going to check if this circuit is stable? What are you going to do? What are a few of the tests you might run? Okay, there we go. So first you said you're going to figure out the poles and zeros. Now, by the way, do you mean when you said the poles and zeros, do you mean open loop, closed loop? Open loop, okay. So we can check the open loop poles and zeros. And then you said something else after that.
Well, check the phase margin.
Okay, there we go. You could check the phase margin once you've done that. That's indeed the very common thing to do. Anything else? What other kind of stability tests did you guys learn about? There's at least one other kind of margin that I'm sure you've heard of. Gain margin, okay. There's a gain margin. That's certainly true. Okay, any other tests you guys can think of? By the way, maybe to spur your guys' thinking, when you say that there's a pole and a zero, what are you assuming about the circuit? Yeah, you're assuming it's linear. Anything else? There's a 3-letter acronym that I'm about to... There we go. You're assuming it's linear and time invariant, right? Because when you say there's a pole and a zero, by definition, you have to assume that it's a linear time invariant system. Okay? So now let me ask you guys, is this circuit a linear time invariant system? No. So first of all, it's certainly not linear, because for better or for worse, the transistors are not linear, and if they were linear, then no one would use them. Okay? So transistors are not linear, and I would actually even claim the circuit is not necessarily time invariant either. Okay? Because if you think about it, let's say I changed the temperature, or the temperature changed due to, whatever, the sun or the moon getting closer, whatever it is. Well, circuit would actually change its characteristics, right? So the take-home point here is really that you have to be really careful when you talk about stability, because most of our notions of stability, most of the things we like to think about, particularly as circuit designers, are all only true given that the circuit is actually linear time invariant. Okay? Which in reality is not quite true. Okay? So this is really just sort of saying very similar to this thing to what I just said a second ago, which is that in reality almost all circuits are in fact nonlinear and potentially time varying. Okay? So when you say stability, what you typically actually mean is not necessarily stability in the sense of a pure linear system, but what you actually typically mean is that the circuit goes to some nominal operating point, and we'll call that nominal operating point the origin, as long as there's zero input, and it does so in finite amount of time. Okay? Now when I say the origin, that doesn't literally mean 0 volts at the output or VDD at the output. It means some stable bias condition. Okay? So for those of you guys who sort of like the control theory kind of stuff, this is kind of another way of saying that it's exponentially stable, meaning that if I wait a finite amount of time, it will get, within a certain error bound of whatever that, sort of stable point actually is. Another sort of common way of defining this is that if you feed the circuit with a bounded input, meaning an input that's not infinite, its output will also not be infinite. Okay? Now that one in particular in the context of sort of nonlinear or time-varying circuits is a little bit trickier because if there is a power supply, typically the circuit will indeed actually have a finite output just because the power supply is finite. But typically what it really means is that over some small region of the circuit, there isn't a behavior where it just goes off to infinity, right, until it finally hits the supply rail. Okay? So again, just be really careful when you say stability, because remember that most of the time when you refer to stability, you're thinking of things in the linear time invariant context. And the circuit itself may or may not really be linear time invariant. Okay, so now the question, of course, is, well, what do we do in practice? I don't know too many people who like to do nonlinear time varying math. At least I certainly generally don't. So what you typically, of course, then do is you say, well, look, fine, the circuit really is nonlinear, time varies, but I can usually linearize the circuit given some operating condition. And then I can do all of these sort of procedures that we talked about before, right? So I can look at the poles, I can get the phase margin, I can get the gain margin, and so on and so forth. Okay? So indeed, that is still what we're actually going to do. But we have to remember that this is really only an approximation. Okay? And the reason it's important to remember, or let's say the implication of remembering that it's really only an approximation, is that you can't just do one linear analysis. You can't just say, well, you know, my circuit is always here. I'll analyze exactly the situation. If it's good there, I know it's good. Not true. All right? You actually have to check it over all of the weird conditions that might ever actually pop up. Okay? So in particular, you should check it across different process corners. You should check it across different temperatures. In fact, I even argue you should check it across different power supplies. Okay? In fact, it turns out there's even some more subtle, tricky things that you may even want to check. So let's say your supply voltage was nominally 1.2 volts. And let's say, you know, from a static standpoint, it varied by, I don't know, plus minus 100 millivolts. Okay? So I would argue that even if that's the case, you should still check that the circuit is actually stable with, as an example, 300 millivolts power supply, 400 millivolts power supply, 500, 600, and so on and so forth. Anyone know why I say that? Why am I claiming that you should check it even at numbers that are way outside the spec of what your nominal supply voltage is supposed to be? It's a little bit of a trick question. Yeah, exactly. What happens when the thing is actually being turned on in the first place? Right? So when the thing is being turned on in the first place, the supply voltage won't be whatever it's nominally spec'd to be. It's going to have to start from somewhere and make its way up. Right? Typically it starts from ground and makes its way up. Well, what would happen if, for example, the circuit was unstable while the power supply was starting? Well, if it's unstable, you may not be able to guarantee that it actually gets out of that unstable condition even once the power supply actually settled to whatever it's supposed to be. Because, for example, if it was unstable, that could cause something else to then go unstable, which then, you know, could feed back in some funny way and cause the whole system to just not start up properly. Okay? So again, the take-home message here is you really have to think very carefully about what are all the different conditions under which the circuit might not actually behave the way you expect it to. Okay? And in fact, if you really want to make sure the thing is stable, which by the way is now, you know, a method I'm going to add to the list because this is actually really what you should do. The only sort of, let's say, I shouldn't say foolproof, but the only, let's say, really, truly correct way of checking these things is actually to do a transient simulation. Okay? Because the advantage of doing a transient is that now, even if it's nonlinear, it's time varying, you can just capture all of those effects. Okay? So in particular, again, you guys tell me, if I have some circuit that I know is nonlinear, I know might potentially oscillate, how do you think you would check it using a transient simulation to see that it's not going to oscillate? Or that it's not going to be quote-unquote unstable? What's the typical way you would check that? And again, let's look at the particular circuit that I'm showing on the right over there. Okay, you could certainly test the step response. That's actually a reasonable thing to do. There's kind of, maybe not necessarily simpler, but there's a more, let's say, common type of solution that people come up with as well, which is very much related to the step response. Yeah, there we go. Basically, you just put a pulse of current or voltage or whatever it is into the thing, right? And then if the thing is going to oscillate, well, you'll see that that small pulse caused it to actually start going bonkers, right? And if not, you should see that within a reasonable amount of time, whatever the pulse was went away, right? Basically, you went back to whatever that nominal operating condition actually was, okay? And by the way, you'll actually do this, even if you're designing an oscillator that you intended to actually oscillate, you'll typically check it this same way, just with a reverse outcome, right? You'll put in a pulse and then make sure that it actually does start oscillating rather than getting stuck at a particular bias voltage. Okay? So indeed, transient sims are, you know, make sure you run a few of those, even if you've done extensive small signal simulations, just as a final double check to really make sure that it's not going to behave strangely due to the fact that it's not really an LTI circuit. Okay? Okay, any questions on that? Or? All right, so now let's sort of, again, think more carefully about how we're really going to sort of check this stability. So let's again assume that for now we've bought into just doing some linearized checks. And we're, again, of course, going to do this over many different bias conditions. But in each particular bias condition, there's still actually a little bit of, let's say, fun that you have in really setting these checks up, right? So as usual, as I'm sure you guys hopefully all know, right, the stability is, of course, still set by that so-called T of S, which, just as a reminder in this case, if before I had defined T is just AV times F, T of F is just AV of S times F of S. Okay, so everything is just now frequency dependent rather than static gains. Okay? So indeed, if I'm going to check, for example, that T of S, that it's because it's an open loop parameter, I generally have to break the feedback loop somewhere, right? Because, I built a circuit that has a feedback loop in it, and if I want to check the actual open loop thing, well, I have to break the loop. Okay? Well, in hand analysis, that's usually a pretty easy thing to do. But maybe just before we get into that, let me again ask you guys a question. So, what was the sort of rule that you were told about where to break the feedback loop when you were doing either hand or even simulation analysis? Yeah, we always said to break it at a high impedance node. Why is it we said that? Why is it important to break it at a high impedance quote-unquote node? Yeah, exactly. You don't want to change the loading, right? Because if I break it at a node that's not high impedance, and by the way, here high actually technically should mean infinite, right? If I don't break it at an infinite impedance node, then I will mess up the loading. Okay? So we're going to say a lot more about that in 1 second. Oh, yeah, question? Okay, so the question was, couldn't you just take the loading and put it back on there? We're going to come back to that in 1 second. Okay, so indeed, let's say there's some hacks we're going to try and play to do exactly that, but we'll come back to it in a second. Okay, it's a very good question. So, by the way, just to make sure it's absolutely clear, in the analysis, if I'm analyzing this circuit, where is it I actually broke the feedback loop to draw that small signal model on the right? At what point in the circuit did I break the loop? Yeah, I broke it at the gate of the transistor. Okay? But now let's think a little bit more carefully about what we really did. So, as we had discussed actually, not too long ago, anytime you have that transistor symbol there, particularly in SPICE, what other elements get added to the input structure that are going to be there whether you like them or not? What other parasitics are there associated with the transistor? That is true. Let's even ignore that. I mean, intrinsically associated with an MOS transistor. What is always the impedance? What is there associated with the input? Yeah, CGS. Anything else? CGD, right? Okay, so now, to be totally clear, when we broke this feedback loop, particularly analytically, what you'd want to do is if this was CGD and this was CGS, you would want to break it inside of that CGS and CGD, right? Because if, for example, you really did it the way I drew there, then our small signal model now would have a CGD here, and an additional CGS there, right? But notice that's actually okay, because in the real feedback loop, indeed those CGS and CGD would also be there. And notice that the way I broke the small signal loop here was I literally broke it inside of the transistor, right? I broke it at the connection to the GM, right? Because if I had just this original picture, then this GM, rather than being multiplied by some test source that I'm imposing, and let me maybe actually draw it on the picture on the left just to make sure it's clear. Right? So what I literally did in that small signal model there was I broke the loop here inside of the CGS and CGD. I added in this test source there, and then I measured the feedback right to the left of it. Right? And again, if you look at the small signal model, that's done purely by, instead of having this GM driven by VFB, I just split those two out. Right? I drove a test source right into the GM, and then I measured the feedback that would have come back into the GM. Okay? this make sense to everybody? Or? Now, why did I spend all this time on this? Well, this is really easy to do analytically, right? It's really easy for me to just say, hey, this feedback thing here is a separate voltage. It has nothing to do with what's going into the GM. But in simulation, is there any way for you to chop off that CGS and CGD there? Or no? No, right? It's just inside of the transistor model. So unless you go into the transistor model and start hacking with it, you're going to get a CGS and CGD every single time you put the transistor down. And all you're going to be able to do is actually try and sort of work around it. Okay, so again, just to make sure that that's absolutely clear, right? Notice this is the sort of small signal model that we wanted, right? Where again, the CGD actually ends up showing up in parallel with the CF. The CGS ends up showing up in parallel with the CS. Well, if we tried to do this sort of in SPICE, literally just by cutting the loop right there and adding a v-test like this, let's draw what that small signal model would actually look like. Okay? So again, of course, I would have the GM. That would indeed be driven by some v-test. Let me call that VT here. I will indeed have an RO. And I will indeed have a C load. Okay? Okay, if I draw the sort of... Well, okay, so now you guys tell me, what would the rest of the model look like if I literally just did this in SPICE? So I just took a transistor, I drove its gate with VT, and then I measured the feedback back to this point right here. What would the rest of the small signal model look like? Okay, well, so let's be a little bit careful. You said there's going to be a CGD connected to right there. And then what's this side of CGD going to be connected to?
Oh.
Yeah, it's going to be connected to v-test. Right? How about CGS? Where does that show up? Yeah, right here. Right, so that's going to be CGS. All right, now how about the rest of the feedback structure? What's that going to be? Yeah, exactly. You'll have a CF over here, a CS over there, and that will be VFB, right? Notice, by the way, I just flipped which side I put the CF and CS versus this picture, but they're obviously totally equivalent, okay? But notice this circuit here is most definitely not the same as this, right? Or this feedback transfer function, most definitely not the same, right? In particular, CGS just got completely knocked out, right? Because we drove it with a voltage source. And as Rachel was saying earlier, even that CGD is not really being properly handled, right? So again, the real key point here is that if I want to do this in SPICE, I now have a problem, okay? Because I can't just break the connection there. I've actually messed up the loading, okay? So now let me ask you guys, and in fact, the suggestion was already made. But let's see if we can really sort of walk all the way through this. And let me draw sort of a slightly different circuit to see if we can get the general concept, and actually that circuit will just make the general concept a little bit more clear. Let's say that I'm indeed going to try and simulate the stability of this unity gain feedback buffer here. Okay? So I just have something like this. Okay, so we've already said that if I'm not careful, I'm going to get things messed up with the loading. But it actually turns out that if I'm not careful, it's not even just the loading that will be messed up, it's actually even the DC bias that will get messed up. Okay? So whatever we do, we're going to have to sort of do very carefully to try and fix both of those problems. All right? So now, you guys tell me, what can I do to this sort of unity gain buffer feedback circuit to basically hack it to try and solve both of those problems? And by the way, this is really a hack in the sense that this is only something you can do in SPICE and not in real life. But that's okay. We're just trying to use SPICE to actually estimate things that we really care about. Okay? So what's a hack you can do, for example, to make it so you can actually fix the DC bias, but still decouple the feedback from the input? What do you guys think? There we go. You said put a really big inductor in, right? Okay, so just to be clear where we would put that inductor in, let me sort of give a little bit of the setup. So let's say that I want to measure the feedback out over there, and I want to apply the v-test right there. Okay, so when I said v in here, really that's going to be sort of incrementally speaking ground. Okay? So how would I place a really big inductor to allow me to apply v-test on one side and measure v-feedback on the other? Where should it be connected? Like, what should be connected between? Yeah, exactly. So I put a really big inductor here, like this, and let me label that L big. And when I say big, I really mean big, like, you know, a Henry or something like that. Okay, again, this is SPICE, so there's no problem with actually doing it. Okay, so by putting that really big inductor in, what did I do? Well, if you think about it, the really big inductor is saying, well, at DC, those two things are connected to each other, right? It's just a dead short. So that means the DC biasing will be correct. But at any reasonable frequency, especially if my inductor is really, really big, I'll basically have an open circuit between those two ports, right? If I have an open circuit, then what's the only other trick I need to apply to allow myself to actually apply the test signal? What else do I have to add in? I heard somebody say something. Oh, okay. We'll get back to fixing the loading in a second. You said the loading is still maybe not correct. That's absolutely true. What else do I have to do? Just even to get the test signal in the first place.
Like a big capacitor.
There we go. I put a big capacitor here, and I apply v-test on that side. So just to be clear, I put my voltage source here like this. Okay? Where again, the whole trick here is that I'm just saying, well, all right, I don't want to mess up the DC biasing, so I can't just drive the voltage source directly. Instead, I'll put a cap in between, and then I know that at any frequency where, and again, by the way, that cap is, of course, big. So just an example, let's say 1 farad or something like that. Okay? I just put the cap in, again, to make sure that, you know, once I've sort of gone away from DC, I can actually apply that test source directly into the input. Okay? By the way, just for those of you guys who haven't heard of this before, this LC structure that I've drawn here is what's known as a bias T. Okay? Because it allows you to apply a DC bias to a node, but independently apply an AC signal. Okay? All right, so this allows us to indeed get the DC biasing correct while still applying a sort of independent test signal and breaking the feedback loop. But we also said that the loading was messed up. So how do I fix that? What should I do to try and fix the loading now? And again, this is totally a SPICE hack. So how can I mimic the loading to try and make it about right? Yeah, exactly. So I basically take another thing like this and put that same amplifier over there, right? Now, by the way, when you said same copy, or a copy of that, did you mean copy of just the amplifier, a copy of the whole bias T, or, you know, what exactly did you mean? Okay, sounds good to me. So we put another V in over here, right? And now, to zero order, this would indeed copy the input parasitics. Okay? So this is a pretty good solution. But unfortunately, it's still not quite right. Or it's still not perfect. So now you guys tell me, what's not quite perfect about this? Yeah?
Can you say a few words about the, like, I guess, input inputsing in terms of, because it doesn't necessarily be a perfectly zero resistance on that.
So you said a couple of things there which may have been sort of getting at the direction that I was asking about. So notice that when I connected this secondary op-amp over here, I also tied it to V in, right? So at least at DC, the sort of positive side should be seeing the same thing as the real op-amp would have been seeing, right? But there is one node on this particular copy structure here, which unfortunately is not quite right. In other words, which will not necessarily behave exactly the same way as this one over here did. So which node is that? Yeah, it's the output, right? Because notice the output, it's totally open loop. It's not necessarily driving anything else, right? And if there's any interaction there, then it's not going to be quite right. Okay? So in particular, if you have, for example, a CGD or just some feed-forward path there, then indeed you will not be mimicking the loading exactly correctly. Okay? Now, it turns out what I've drawn here is actually usually pretty good in that as long as you don't have very big feed-forward, you can actually get very close to the sort of ideal result. But nonetheless, it's never really quite perfect. In fact, okay, I've never proven this, but I think with something like what I'm showing, it's kind of impossible to actually get it exactly right. Okay, because every time you try and fix it, you end up adding another copy, and then the copy is also not quite right, and so you just end up with sort of an infinite recursive loop. Obviously, eventually the errors are small enough that maybe you don't care about them, but nonetheless, methodologically, this is not necessarily the ideal way of doing it. Okay? So the good news is that there's actually a way of fixing this. Yeah, question?
Sorry,
No problem.
like adding that capacitor in is suddenly.
I'm not adding a capacitor here. I was just saying if inside of the amplifier there was actually a capacitor intrinsically, then that would actually cause a problem. That's what I was getting at.
The other thing I was wondering about is, do you need to add loading onto the VT side?
Onto the VT side.
To the input side, so like the input in the feedback loop would seem like some small finite.
Oh, so the question was, do you have to add any loading here? The answer is no, because I am driving that with a voltage source now. Right? So I just have to make sure that I'm mimicking the loading on the output of the op amp. Right? And by the way, that's again why usually you really want to break the loop at these high impedance nodes. Because if you break it at a high impedance node, you know that driving it with a voltage source doesn't matter because it didn't change anything. And you know that the feedback was driving an infinite impedance, so that also didn't change anything. Right? Okay. So the bad news here is that, again, it's tough to really do this exactly correctly. The good news is there's a trick or there's a method you can use to actually do this right. Okay? So that method is what's called Middlebrook's method. This was invented actually quite some time ago, almost 40 years ago now, in 1975. Middlebrook was on the faculty at Caltech for a very long time. And the idea is actually pretty straightforward. Okay? And it basically goes something like the following. So what Middlebrook basically said was that let's say that controlled current source that I'm showing there is the GM that we care about. Okay, and as an example, it's controlled by Vx, which is just defined over here on the left. Okay? And it's going to be the same GM right here. So the technique that Middlebrook came up with is the following. He basically said, you know what? I can't ever get the loading exactly right by playing these copying tricks. So instead, let me break the loop in a slightly different way. And in fact, let me break it in two different ways. Measure the information I can get from each of those two different sort of transfer function measurements. And then just combine them to end up with, at the end, something that I know is provably correct. All right? So in particular, what he did was the following. He said, well, if this was my sort of controlled current source here, let me first break the loop by inserting a voltage source. Okay, this V-test. And what I will measure is when I apply this V-test, I will measure the ratio between the output voltage Vy and the input voltage Vx. Okay? And again, I can just measure that totally in SPICE. Right? The next thing I do is I'll reclose the feedback loop. So I'll connect sort of the feedback side back to the output of the amplifier. But now let me apply a current source, basically sort of, you can almost think of it conceptually in parallel with that particular connection. Okay? And let me again measure another transfer function, which in this case will be the ratio of the current flowing into the amplifier versus the current flowing back through the input network. Okay? So that's just going to be these two transfer functions. The first I'm going to call this TV. The second I'm going to call that TI. Okay? And as I'm indicating the equations here, which by the way are not super critical, I can calculate exactly what those transfer functions would be as a function of the impedance on the two sides. The reason this then becomes useful is because I know what the true loop gain actually was as a function of those impedances. So it turns out that actually by taking these two measurements, I have all the information I need to compute what this real transfer function actually is. And at the end of the day, it just turns out to be TVTI minus 1 divided by TV plus TI plus 2. Okay? It's some simple math, some simple algebra to just get from these two expressions to this one and how you sort of end up with this particular solution. Okay? Now, by the way, the details of exactly this expression are not super critical. Again, I encourage you to work them out on your own. It's not too difficult to do. But the more important point is that, indeed, we now actually can have a method that will give us something that, at least ideally speaking, would be the perfect, correct result. It will take into account all of the loading absolutely correctly and can actually be done in simulation. Okay? There are a couple of points that I want to mention here. The first is that this problem of sort of checking stability exactly correctly was known for quite some time. As you can tell, Middlebrook came up with a way of doing this, back in the 1970s or so. And so in the more recent versions of SPICE or Spectre, there's a new type of analysis that's called .stb, which it doesn't exactly use Middlebrook for methods for reasons that I'll explain in 1 second, but it uses a very similar method to exactly do these stability calculations in a very, very accurate way, meaning that it will not get screwed up by these loading effects, all right, or lack of loading effects. So, good thing to know about, because again, from sort of here on out, if you need to really do a stability analysis, .stb is basically the way you should do it. Now, if you happen to be unfortunate and you only can use HSPICE or some other version of simulator that doesn't actually have these analyses built into it, that's why I actually covered this, so that you know how you can do it even in SPICE yourself. Okay? The only other thing that I want to mention just briefly here is that if you'll notice, at the end of the day, the way I'm actually calculating my final loop transfer function is I have to do some math on two quantities that I measured, right? And in particular, I have to multiply together these two loop transfer functions and then subtract one on the top. Okay? So here's where you now have to start remembering that, SPICE and pretty much anything else you do on the computer always has only a certain degree of accuracy associated with it. All right? And in particular, if you take two big numbers and multiply them and then subtract another number and the end result ends up being something very, very small, you have to be worried about the numerical accuracy of the simulator. Okay? Because indeed, you can get some very big errors anytime you have those kinds of situations if internally under the hood things are not handled very, very carefully. Okay? And Middlebrook's method is particularly susceptible to this largely because of the sort of multiplication subtractions that you have to do to actually get the final result. So there are actually other methods that are a little bit more robust from this standpoint, which, again, I can sort of cover if people are interested. But even independent of that, let me maybe ask you guys now, let's say that indeed you had a simulator or you yourself used Middlebrook's method, and you wanted to know whether or not the result you got is sort of trustworthy, meaning that even despite any numerical accuracy issues, you're still getting a pretty reasonable estimate of the final transfer function. What experiment would you try to check if your thing is basically doing okay? What would you do? Yeah, this is very practical.
You'd actually close the loop and compare the closed loop responses.
Okay, you could indeed close the loop and then simulate the closed loop response and see if those things match each other. That is true, although that one's also a little bit tricky. Because, for example, if I have a very high gain structure, the errors you're looking for may be indeed very small in the closed loop. And so it may be hard to actually tell from the closed loop response how much of an error you had in the open loop response. There's another even simpler thing that you can do. That's not a bad solution, by the way, but there's another even simpler thing that you can do. Again, very, very practical. Any of you guys ever heard of RELTOL or ABSTOL? No one's heard of these? Raise your hand if you've heard of RELTOL or ABSTOL. Okay, you've at least seen them at some point. Okay, so any simulator always has internal settings associated with its accuracy. In particular, it has things like the relative tolerance, that's RELTOL, and the absolute tolerance, ABSTOL. Okay? So maybe just as a, since I mentioned these, what do you think you would do to those parameters to try and check if your calculations were actually reasonable? What's the sort of procedure you'd follow? And by the way, the more you crank up those parameters, the more accurate the simulation gets. So what do you think you guys would do? Yeah, exactly. So, by the way, you have to be careful when you say big and small, because, in some cases, making the parameter number small is actually more accurate. But basically, you'd crank up the accuracy of the simulator, or to be more clear, you'd start out, you'd run a simulation with whatever your default setting was, right? And then if you're not sure if it's really accurate, you say, oh, well, okay, let me crank up the accuracy, right? If you crank up the accuracy and you see that nothing really changed, pretty reasonable indication that things are reasonable, right? If, on the other hand, you crank up the accuracy and you see that things are changing all, in a very big way, that's an indication that actually you didn't have an accurate enough simulation in the first place. So then what you do is, of course, you'd crank up the accuracy until, again, you see that the simulation results are not changing anymore. Once they're not changing, again, reasonable indication that your final result is kind of okay from an accuracy standpoint. Okay? So again, keep this in mind because these kind of accuracy issues, I mentioned it here in the context of this feedback circuit, but this pops up all the time. Okay? There's a lot of things that you will care about that could be on the edge of the nominal accuracy of the simulator. And so you better actually play around with those parameters to ensure that what you're seeing is real and not just some artifact of numerical garbage coming from the calculations. Okay? By the way, just as another thing to mention, hopefully briefly so you guys know about it, in SPICE in particular, there's something called, or there's an option you can set that basically says .option accurate, which automatically retunes a lot of the simulation parameters to try and improve the accuracy of the simulation. So a lot of times, again, for things that you really care about, you'll just go and add this .option accurate in, just so that by default you'll get sort of a better estimate of things. Now, by the way, why is it that you don't necessarily always want to have this option on? Yeah, it just can take longer to actually do the simulation, right? And for stuff that, maybe it doesn't really matter, the default accuracy is good enough, it'll run a lot faster if you don't do this, okay? So I mention this because, again, this option is a useful one to actually use, but nonetheless, be careful because there are indeed going to be situations where even with that option on, your simulation will still not be accurate enough to actually answer the questions you're interested in, okay? So anytime you run into those potential kind of things, especially if you see something just physically that doesn't make sense, crank up those accuracy parameters and check that it actually behaves the way it's supposed to.
Is there a good way of done? I feel like something you can crank up. I've seen simulations where you crank up the accuracy and still can't converge, even though maybe physically you should be able to converge.
Okay.
Is there a good way? I mean, I think like the example I saw a lot is the when they have that 8 to 100 amplifier, like you can crank up that amplifier gain a lot, like create problems. Are there good places to sort of check if you're getting that kind of simulation? Like, how can I kind of fix the convergence?
Okay, so the question was about basically DC convergence. And if there's any sort of useful, let's say, tricks or tips in terms of looking at what's causing it to not actually converge at DC. It turns out the DC convergence is a pretty big topic in general in simulators because that's one of the hardest steps that it has to take to actually just get anything really working. There's unfortunately no great, let's say, tools within SPICE itself to tell you, oh, okay, this was the particular convergence issue that I had. But there is one really big hammer that, on occasion I have used. The big hammer is start everything at 0 and slowly ramp it up. Because usually, unless things are really bad, which occasionally they are, usually if things are kind of reasonable in terms of the internal models, everything should be stable at 0 because pretty much nothing is happening. And then as you start ramping up, it'll slowly go from the reasonable DC bias point up to something that should hopefully be corresponding with reality. Now, even there, you have to be careful because it may unfortunately converge to something else, right? Or it may actually barf in the middle of you ramping the supply like that. But that's kind of typically the biggest hammer for getting around some of those convergence issues. All right, other questions on this? Or? Okay, so I think we'll basically end with that for today. Just as a reminder, there's not going to be any lecture on Thursday since we're just going to be having the midterm. I'll probably hold some extra office hours or something like that, but I'll post that up on Piazza. And also as a reminder, the review session will be tonight at 6 p.m. just here in 550 Corey. So see you guys all then, and good luck on the exam.